Hi, I'm Aditi from Data's Good, and I thank you for joining us today. At Data's Good, we've trained thousands of students in our live classes and helped them make successful data science careers. I welcome you to this full course of clustering analysis. In this clustering analysis full course, we'll see the introduction and implementation of k-means clustering, hierarchical clustering, DBSCAN clustering, BIRCH clustering, CURE clustering, and many more. To download the resources of this course, a link is given in the description. So before we begin, make sure you have subscribed to our channel and also don't forget to hit the bell icon to stay updated with all the latest videos coming from Data's Good YouTube channel. So we are going to understand about one of the most important applications of machine learning, that is clustering analysis. Clustering analysis is a branch of unsupervised machine learning. Now, if you do not understand what is the meaning of unsupervised, let me explain. Unsupervised learning is a technique of learning the patterns without any labels or assistance. In simpler words, the model tries to find out patterns from the data without any training. If you would have learned about the supervised learning, you must have seen that the machine learning models need to get trained on a training data to give predictions. But here in unsupervised learning, there is no need for training the model. The model will learn on its own by finding common patterns amongst the data. Now you must have got one big question in your mind. How do we evaluate the performance of unsupervised models? Because these models learn on their own, hence there is a possibility that these models might make a mistake. How are we going to track down the mistakes committed by these unsupervised models? The answer to this is simple. We cannot evaluate the performance of unsupervised models, but we can use our business sense to judge whether the predictions are good or not. This means we'll have to use unsupervised models very carefully. Now that we know that we have to be careful while performing clustering analysis, let's go understand the technical definition for clustering analysis. Clustering is a technique that involves grouping of similar data points. When a set of data points is provided, we can use a clustering algorithm to classify each data point into a specific group. In theory, data points that are in the same group should exhibit similar features, while data points in different groups exhibit dissimilar properties and features. Now let's understand types of clustering. Broadly speaking, clustering can be divided into two subgroups, that is hard clustering and soft clustering. Starting with hard clustering, it is a type of clustering analysis where each data point either belongs to a cluster completely or not. This means every data point will belong to only one cluster at a time. Now, soft clustering. It's a type of clustering analysis where a data point can belong to multiple clusters at the same time. This means that using soft clustering, we can have our data points associated to multiple clusters at the same time. Now, in most of the cases, we'll prefer hard clustering as we want every data point to be in one cluster only. But there will be special cases where soft clustering can also be preferred. Apart from hard clustering and soft clustering, there are some more types of clustering. Let's discuss those models as well. Starting with the connectivity models. These models work on the basis of distance. These models assume that if the two data points are closer to each other, they are similar to each other, which means the data points lying closer to each other will be grouped together in one cluster, and the data points lying far from each other will be separated in different clusters. Now let's talk about next type of clustering model, which is Centroid model. These models work on the notion that similarity is derived by the closeness of a data point to the centroid of the clusters. One of the most famous algorithms that fall under this category is k-means algorithm. The next type of clustering model is density-based models. These models cluster the data points by finding areas of varied density and assigning data points to these different density regions. One of the most famous algorithms that fall under the category is DBSCAN. Now we'll talk about the most popular and amazing applications of clustering analysis. Starting with the applications in the field of sales and marketing. Most of the companies who are trying to get the best return on their marketing ads expenditure and campaigns, it's crucial for them to target the right audience. And clustering analysis can help these business organizations to keep a track of their target customers and save a lot of money. Clustering analysis will help you by grouping people together with similar traits and likelihood to buy a product by using their characteristics. Another interesting application is to track down fraudulency. You heard it right. Clustering analysis can help by analyzing the fraudulent patterns and then clustering all the similar data points so that we can keep track of fraudulency in the easiest manner. I know you would also have got some ideas on how clustering analysis can be used for solving real-world problems. You can post down your ideas in the forums and we'll tell you how your ideas could be implemented. Sounds interesting? So don't forget to post your ideas on the forums. Now, coming back to the applications of clustering analysis, we know that there are so many real-world problems that could be solved by using clustering analysis. So let me just put it out simply to you. The other major applications are fake news detection by clustering the fake news together, spam mails filtering by clustering the spam mails together, finding distinct groups for email marketing and follow-ups, finding distinct groups for providing offers and benefits to customers, finding distinct groups for making coaching groups for students, and many more. Now we're going to learn about elbow method, using the elbow method for choosing the best value for K. Now before learning the K-means clustering algorithm, we have to understand the meaning of K in K-means clustering algorithm. The K in K-means algorithm is simply the number of clusters which we want from our data set. Now, as we know that prior implementing the K-means clustering algorithm, we have to find the optimal value for K. Because if we do not find the best or optimal value for K in K-means algorithm, we might end up getting wrong results. Now, the big question which you must have got in your mind is that, how are we going to find it? So, for finding the best or optimal value of K in K-means clustering, we can use the elbow method. Let's try to understand how this elbow method is going to help us find the best value of K for implementing K-means clustering analysis. The elbow method is a heuristic method. In this method, we plot the explained variation against the number of clusters and finally picking the elbow of the curve as the number of clusters to use. Now, what if we have multiple elbows in the curve? We'll have to pick the last elbow. The point where we find the elbow will be the number of clusters we will use for our K-means clustering. Now let's try to understand this approach by taking this example. Here you can see that in the y-axis we have the number of clusters starting from 1 to 10. And in the x-axis we have the variance. Now if you take a closer look at the chart, you can see the two elbows in the chart. The first elbow occurs at 3 and the second elbow occurs at 5. Now if you remember, we had already discussed that we have to choose the last elbow. Hence our optimal number of clusters would be 5 to implement the K-means clustering analysis. Introduction to K-means clustering now. K-means algorithm is a Centroid-based algorithm. It tries to make the intra-cluster data points as similar as possible, while also keeping the clusters as different as possible. It assigns data points to a cluster such that the sum of the squared distance between the data points and the cluster's centroid minimum. The less variation we have within clusters, the more homogeneous the data points are within the same cluster. Now let's take a look at how the K-means clustering works by looking at this image. We have produced this image by using the mglearn package. Using this package, we can visualize the working of any machine learning algorithm. Let's try to understand the K-means algorithm step by step. First, you can see that we have some input data. We have considered the value of K as 3. which means that we are going to have 3 clusters in this data. After this, we are going to initialize 3 centroids at random. You can see 3 centroids in red, blue, and green color. And for assigning the points, you will have to calculate the distance of all the white points from the red, the blue, and the green centroids. After calculating the distance of each of the points with 3 centroids, color the white data points in the color of centroid to which they are closest to. After assigning the points, we have to recompute the centroid as they have to be placed in the center of their respective clusters. Now, as the position of these centroids have changed, we have to reassign the points again in the same way we did before. Now, you can see that there is some change in the clusters. As the clusters have changed again, the centroids of these clusters will be recomputed, and then again these points will be assigned. Now you can see that the centroids are in the middle. Hence, we can say that the clusters are ready. So this is how the clustering analysis works. Now, we are ready to take up a real-world problem as a challenge and solve it using the k-means clustering algorithm. And for that, we are going to take up the mall customers data set. You can find this data set in the resources section. If you face any difficulty to find the data set, do contact your mentor. So let's go to the resources section, download the data set. After we download, we'll have to unzip the data set. Now let's open our Jupyter notebook. You can see that our Jupyter notebook has opened successfully in the Chrome browser. Now we'll click on the new button and select the folder option. After clicking on the folder option, we can see that an untitled folder is created. We can rename this folder to Mail Customer Segmentation. As in this project, we are going to segment or cluster the mall customers based on their characteristics. Now get inside this folder, click on the Upload button and upload the mall dataset that we just downloaded from the resources section. After the dataset is successfully uploaded, we'll have to create a Jupyter notebook by clicking on the New button and selecting Python option. Yes, our Jupyter notebook has opened successfully. Now the first step is to import all the required libraries such as NumPy, which is going to help us for mathematical operations, Pandas, which is going to help us for data frame operations, and finally Seaborn and Matplotlib for data visualizations. If you've not installed all of these libraries yet, you can take a pause and install all of these libraries by using the pip installer. All the libraries are perfectly imported. Now the next step is to import the dataset into this notebook. To import the dataset, we are going to use the read CSV function available in the Pandas library. Let's also check the shape of the dataset by using the shape attribute. We can see that there are only 200 rows and 5 columns in this dataset. Let's also take a look at the top 5 rows of this dataset by using the head function. We can see that 5 columns are customer ID, gender, age, annual income, and the spending score. Now that we have seen the columns in the dataset, let's discuss the problem statement. The problem is to find the distinct groups of customers present in the mall data. These distinct groups will help the marketing team to find out the target customers. Not only that, but it will also help the marketing team to make special attractive offers to customers belonging to different clusters. So now that we know that we have to cluster the data to help the marketing team for better targeting and follow-ups, the big question is, which of the characteristics of the customer should be chosen for creating clusters? Any guesses? Well, according to me, the most important characteristic of a customer for the marketing team would be their annual income and spending score. Hooray! We cracked the problem statement. Finally, we came to the conclusion that we will be using the annual income and spending score of the customers to create clusters from the dataset. First of all, as we decided to create the clusters using the spending score and the annual income of the customers, let's visualize the relation between these two characteristics of a customer using a scatter plot available in the Seaborn library. Taking a closer look at the scatter plot, for annual income versus spending score, we can see that there are 5 clusters visible. Now the question is, if we decide the number of clusters by taking a look at the scatter plot, why do we need the elbow chart then? So sometimes it'll be easy for you to find the number of clusters for your clustering analysis, but when you will have a lot of data to cluster, in that case, you might not be able to find out the best value of K or number of clusters. Remember that Daniel Kahneman said that never trust your gut or instincts. They can be wrong also. And that's why we are going to use the elbow method for deciding the number of clusters for our analysis. So let's get started and prepare our data for the analysis. We are going to create a set of data which will only consist of the columns which we want to use for our analysis. Now, using the LOC attribute, we'll select only the annual income and spending score columns and save it in a variable called X. You can see that the shape of X is 200, 2, which means it has only 2 columns. We have to find the optimal number of clusters by using the elbow method. The elbow method calculates the within cluster sum of squared errors for different values of K and chooses that value of K for which the WSS value starts to diminish in the plot of WSS versus K. This is visible as an elbow. To implement the elbow method, first we'll import the k-means algorithm from the sklearn.cluster module. After that, we'll create an empty list for storing the WCSS values. We'll iterate from 1 to 10 to obtain the best value of K. And finally, we can see that elbow chart is ready. We've already discussed how to choose the best value for K. We can see that the last elbow occurs at 5. Hence, the optimal number of clusters for our analysis will be 5. Now we are ready to implement our k-means clustering analysis. This time we'll specify the n cluster parameter with 5 and rest of the parameter will be as it is. Now to get the clusters, we'll use the fitPredict function and store our results in a variable called ymeans. Let's visualize these clusters by using a scatter plot. Here you can see that we have 5 different values for ymeans, which is 0, 1, 2, 3, 4. These are nothing but labels for the 5 different clusters that we have just created using our k-means clustering algorithm. Also for the x-axis, we are specifying annual income, which is encoded as 0, and the spending score, which is specified in the y-axis, is encoded as 1. We have specified different colors for different clusters to identify them easily. After identifying and understanding these clusters, we're also specifying interesting labels to these clusters, which is completely optional. Now let's discuss the inferences which we get from this plot. The first inference is that we have 5 distinct segments of customers, namely miser, gentle, target, spendthrift, and careful, based on their annual income and spending score. Now we're going to use silhouette score to analyze the clusters, which is heuristic, which means it is highly appropriate but not correct exactly. We created 5 clusters out of the data. We also know that we do not have any evaluation metric for analyzing the accuracy of unsupervised machine learning algorithms. So the big question is, how are we going to achieve confidence on the solution we just got in the previous lesson using the most popular k-means clustering algorithm? To answer this, in this lesson, we are going to learn about the silhouette score. So let's first try to understand how the silhouette score is going to help us evaluate our clusters. Silhouette score is a value which lies in the range of -1 to 1. A value of +1 indicates that the number of clusters we have built is perfect. Similarly, the value of -1 indicates that the point is close to its neighboring cluster than to the cluster it's assigned, which means it's a complete disaster. And finally, a value of 0 means that the data points are at the boundary of the distance between the 2 clusters, which means that the results are poor. Now we conclude that a silhouette value of +1 is ideal and -1 is least preferred. Hence, the higher the value, better is the cluster configuration. Now, let's understand how does this silhouette method works. The silhouette method is a way to measure how close each point in a cluster is to the points in its neighboring clusters. It's a neat way to find out the optimum value of K during K-means clustering. Briefly, it measures the quality of clustering. This means that the silhouette method determines how well each data point lies within its cluster. For that, we'll have to come back to the Jupyter notebook. We'll start from where we left the last time. You'll see the last time we obtained these 5 clusters. And now using the silhouette method, we are going to validate our results. To implement the silhouette method, we'll have to import it from the sklearn.matrix package. After it's imported, we'll have to specify the dataset used for clustering, which is X, as a first parameter, and then the labels for the clusters that we created using clustering analysis as a second parameter. Now the last parameter is the metric, where we'll specify Euclidean, so that the silhouette method uses the Euclidean method for calculating the distance between 2 data points. You can see that the score is coming out to be 0.554, which is not so bad. We can say that our clustering method is good. Now, to be more confident of the choice for number of clusters, the silhouette method helps us to visualize the silhouette score for each number of clusters in a chart. You can get the silhouette visualizer from the Yellow Brick library. This is an amazing machine learning library which can help us to visualize the black box models. So let's first install this library. To install it, first of all, we'll have to open your command prompt, and now you will have to type pip install Yellow Brick. Then press enter. It'll take some time to install, and after it gets installed, you can come back to your Jupyter notebook. Now, for the people who are getting errors while importing this library, should contact their mentors and get this issue resolved. Let's come back and import the silhouette visualizer from the Yellow Brick library. And then plot the graph for 2, 3, 4, and 5 clusters. It's done. You can see that the chart is finally produced. You can take a closer look at the first chart for 2 clusters. The silhouette score is around 0.3. And for 3 clusters, the silhouette score is around 4.7. Similarly, for 4 clusters, the silhouette score is around 4.9. But the silhouette score is around 5.6 for 5 clusters. That means our choice of 5 clusters is the best. You also got to witness that the choice of 5 clusters was the best choice for segmenting the mall customers. Now, if you remember, we also raised a question that can we perform clustering analysis on more than 2 features at the same time? To answer this question, we are here. We can cluster any number of features at the same time, but we cannot visualize our clusters. For 2 features, we need a 2-dimensional scatter plot. And for 3 features, we need a 3-dimensional scatter plot. Similarly, for visualizing a cluster of 4 features, we need a scatter plot having 4 dimensions, which is impossible. That means we can perform clustering analysis to any number of features, but we can visualize the clusters only for 2 and 3 clusters. So let's try performing the clustering analysis on the whole mall dataset. For that, let's get back to our Jupyter notebook. Let's check the head of the dataset. We can see that gender column is categorical in nature, and we cannot perform clustering on a categorical column. Now, the customer ID is a column which consists of unique ID for each one of the customers. Hence, we will ignore the customer ID and gender columns in this case. Let's create a data for performing clustering. This time we'll include age, annual income, and spending score. After that, we'll use the elbow method for determining the optimum number of clusters. Looking at the elbow chart, you can see that there are 3 elbows this time, and the last elbow is at the number 6. Hence, we will have 6 clusters for our analysis. Now, we can define our k-means clustering algorithm with 6 clusters and then get the prediction stored at y-means. Now, last time we visualized our clusters, but this time we have 3 dimensions, and it would be really very difficult for us to see our clusters in 3 dimensions. So instead, we'll concat the clusters in our data, and we'll check the customer IDs for each of the clusters. Hooray! You can see the IDs of all the customers from each of the clusters. It was so satisfying, isn't it? I just loved exploring cluster analysis. Now we'll get introduced to hierarchical clustering. You must be thinking that if you already know how to use and implement the k-means clustering algorithm, then what's the use of learning a new algorithm? If you remember, we learned so many algorithms for regression and classification also. All of the algorithms are special in their own way. Hence, it is a good practice to learn new algorithms. It'll help to improve your reasoning while performing clustering analysis the next time. So without wasting time, let's get started and understand the hierarchical clustering algorithm. Hierarchical clustering is an algorithm that groups similar objects into groups called clusters. It creates clusters that have a predetermined ordering from top to bottom or bottom to top. There are 2 types of hierarchical clustering, divisive and agglomerative. Let's first talk about divisive. In a divisive or top-down clustering method, we assign all of the observations to a single cluster and then keep partitioning the cluster to at least 2 similar clusters and so on. Experts say that the divisive algorithm produces more accurate hierarchies as compared to the agglomerative algorithms in some circumstances, but are conceptually very complex. Now let's talk about the agglomerative method. In an agglomerative or bottom-up clustering method, we assign each observation to its own cluster and then compute the similarity between each of the clusters. After that, we join the 2 most similar clusters and so on. So I hope you understood the difference between the divisive and the agglomerative clustering analysis. Now you must be thinking about, how's the distance being measured between these clusters? So let me tell you, there are 3 different methods: single linkage, complete linkage, average linkage, which are used for calculating the distance between the clusters in a hierarchical clustering. Now let's try to understand these methods one by one. First of all, we have the single linkage hierarchical clustering. The distance between 2 clusters is defined as the shortest distance between 2 points in each cluster. Whereas in complete linkage hierarchical clustering, the distance between 2 clusters is defined as the longest distance between 2 points in each cluster. And finally, in average linkage hierarchical clustering, the distance between 2 clusters is defined as the average distance between each point in one cluster to every point in the other cluster. So I hope you understood how hierarchical clustering works and are excited to implement this too. But there is a limitation in hierarchical clustering. We cannot use the elbow method for deciding the optimal number of clusters. For hierarchical clustering, we have to use the dendrograms for deciding the optimal number of clusters. Let's discuss dendrograms. And now it's time for us to plot the dendrograms. But before that, let's know a little bit more about dendrograms. A dendrogram is a diagram that shows the hierarchical relationship between objects. It is most commonly created as an output from hierarchical clustering. The main use of a dendrogram is to work out the best way to allocate objects to clusters. Alright, so dendrograms will represent the hierarchical relationships between the clusters. Now let's plot the dendrograms chart by importing the SCH class from sklearn.cluster.hierarchy. While defining the dendrogram, we'll specify the method as WOD, where WOD is a common agglomerative approach to calculate the distance between 2 clusters. Our dendrogram is ready now, but it seems quite complex. Now the question is, how do we analyze the optimal number of clusters from our analysis by using the dendrogram? The answer to this is simple. We'll have to draw a horizontal line through those linkages, which are the longest. Now let me show it to you. Here we have two different choices. Let's talk about the first choice. The first choice is that we have to draw a horizontal line at 300, cutting the tree lines, which means that the optimal number of clusters will be 3. But the second choice says that we have to draw a horizontal line at 200, cutting 5 lines. Out of 3 lines are green and rest 2 are blue, which means that the optimal number of clusters will be 5. Now the confusion is, which of these two choices is best for us? The best choice is that horizontal line which cuts the longer lines. Now if you take a closer look at the chart, you will notice that the horizontal line at 200, cutting 5 lines, is the best choice. Hence the optimal number of clusters for our analysis will be 5. Now we'll see the implementation of hierarchical clustering. As we know that we need to have 5 clusters for our hierarchical clustering, let's implement the hierarchical clustering algorithm. We will use the agglomerative clustering this time. If you want to, you can try implementing the divisive clustering also. While implementing the agglomerative clustering, we will specify the n cluster parameters as 5, which means we want 5 clusters from the data after performing clustering. And after that, we'll predict the clusters for each of the data points using the fit predict function and store the values in a variable called YHC. Now our algorithm has implemented successfully. It's time for us to visualize these clusters using the scatter plot, the same way we did for k-means clustering. Well, the clusters are created and we can see that the results are very much similar to that of k-means clustering analysis. But remember, this is not going to happen every time, as workings of both the algorithms is much different from each other. So it's crucial for you to now understand when you should choose the k-means algorithm and when you should choose the hierarchical clustering. In most of the cases, whenever the data is in spherical shape, k-means is preferred, whereas the hierarchical clustering is preferred in all the cases where the data is in complex shape. Hierarchical clustering is highly preferred for social network analysis and so many other areas where hierarchies are present within the data set. So I hope you understood the difference between the k-means and hierarchical clustering. It's very important interview question also. Now, one thing you must have noticed, that both of these algorithms require the number of clusters in prior. But what if you get to work on a very large sample of data and determining the number of optimal clusters become impossible? In that case, we can use the DBSCAN clustering algorithm, which is very famous as it can handle very huge data sets. The most important thing about the DBSCAN clustering algorithm is that it does not even require the number of clusters in prior, as it finds out the optimal number of clusters on its own. So our next topic is DBSCAN clustering. The most important thing is that we don't need to provide the number of clusters required in prior. So let's get started and learn more about the DBSCAN clustering. First of all, DBSCAN stands for Density-Based Spatial Clustering of Applications with Noise. The DBSCAN algorithm groups the points together that are close to each other based on a distance measurement, usually Euclidean distance, and a minimum number of points. The DBSCAN algorithm also helps us to track down the outliers as the points that are in low density regions. So by now you must have understood that the DBSCAN algorithm basically requires 2 parameters, which are EPS and midpoints. Let's try to understand these 2 parameters in depth, starting with EPS parameter. This parameter in DBSCAN algorithm specifies how close points should be to each other to be considered a part of a cluster. This means that if the distance between any 2 points is less than or equal to the EPS value specified by us, will be considered as neighbors. This EPS value will act as a threshold for considering 2 points as a neighbor. Talk about second parameter, that is min points. This parameter is used to specify the minimum number of points to form a dense region. For example, if we set the min points parameter as 5, then we need at least 5 points to form a dense region. This sounds so interesting, but before implementing this, let's understand the terminologies related to the DBSCAN clustering algorithm. There are 3 different types of points in the clusters after the DBSCAN clustering is complete. Let's understand them. The first type of point in the cluster is the core. The core is a point that has at least m points within distance n from itself. The second type of point in the cluster is the border. The border is a point that has at least one core point at a distance n. And finally, the noise, which is a point that is neither a core nor a border. It has less than m points within distance n from itself. Finally, let's take a look at the algorithmic steps for DBSCAN. Step 1. Find all the neighbor points within EPS and identify the core points or visited with more than mini points neighbors or visited with more than min points neighbors. Step 2. For each core point, if it is not already assigned to a cluster, create a new cluster. Step 3. Find recursively all its density connected points and assign them to the same cluster as the core point. Step 4. Iterate through the remaining unvisited points in the data set. Those points that do not belong to any cluster are noise. So I hope you enjoyed learning about DBSCAN clustering algorithm. Moving to next part, that is implementation of DBSCAN clustering. We'll perform clustering on the annual income and spending score columns. But before implementing the DBSCAN clustering, we'll have to determine the value of 2 very important parameters of DBSCAN clustering. For determining the value of min samples, we'll follow some simple rules. For 2-dimensional data, we use DBSCAN's default value of min points is equal to 4. If your data has more than 2 dimensions, choose min points is equal to 2 into dim, where dim is equal to the dimensions of your data set. As the dimension of your data set is 2, hence the value for your min samples parameter will be 4. Now we have to determine the value for the epsilon parameter. For calculating the epsilon parameter, we will calculate the distance from each point to its closest neighbor using the nearest neighbors. And after calculating the distances, we just have to sort them and finally plot them. Now you can look at the plot. Now the optimal value for epsilon would be the maximum curvature of the curve, which is around the value 8. Hence we can conclude our epsilon value will be 8 and our minimum sample value will be 4. Now, as we know the parameters for our DBSCAN model, let's implement our DBSCAN clustering model with the epsilon and minimum sample parameters as 8 and 4 respectively. After the model is defined, we can now visualize the clusters defined by the DBSCAN model. Yes, the results are so satisfying. It has identified the right clusters. It has also pointed out the outliers in the data, which is colored in dark blue color. Now we are going to learn and understand the working of another important clustering algorithm, the BIRCH Clustering algorithm. So, start it. To begin with, the most important thing is that it's an unsupervised data mining algorithm used to perform hierarchical clustering over particularly large data sets. First of all, BIRCH stands for Balanced Iterative Reducing and Clustering Using Hierarchies. BIRCH is a clustering algorithm that can cluster large data sets by first generating a small and compact summary of the large data set that retains as much information as possible. Then this smaller summary is clustered instead of clustering the larger data set. Now the big question which you must have in your mind is that how does the BIRCH clustering algorithm work? Let me answer this. We will start with building the CF tree. BIRCH clustering summarizes the large data sets into smaller, dense regions called clustering feature entries. Formally, a clustering feature entry is defined as an ordered triple, n, ls, ss, where n is the number of data points in the cluster, ls is a linear sum of the data points, ss is a squared sum of the data points in the cluster. It's possible for a CF entry to be composed of other CF entries. Optionally, we can condense this initial CF tree into a smaller CF. Then the next phase is global clustering. It applies an existing clustering algorithm on the leaves of the CF tree. Now, as we know that a CF tree is a tree where each leaf node contains a subcluster. Every entry in a CF tree contains a pointer to a child node and a CF entry made up of the sum of CF entries in the child nodes. Optionally, we can define these clusters. Due to this two-step process, BIRCH is also called two-step clustering. Now, by looking at this image, let's try to understand the BIRCH clustering algorithm step by step. So this is how BIRCH clustering algorithm works. Let's discuss the parameters of BIRCH algorithm. As you can see, the first one is threshold. Threshold is the maximum number of data points a subcluster in the leaf node of the CF tree can hold. Then the next is branching factor. This parameter specifies the maximum number of CF subclusters in each node, internal node. And the last one is N clusters. The number of clusters to be returned after the entire BIRCH algorithm is complete, that is, number of clusters after the final clustering step. If it is set to none, the final clustering step is not performed and intermediate clusters are returned. Implementation of BIRCH clustering algorithm, and for that we will use the mall dataset. For that we'll have to get back to our Jupyter notebook. So first, we'll start by loading the important modules. Here you can see that we have imported BIRCH module from sklearn. Now that all the important modules are loaded, we'll create our BIRCH clustering model. Now, if you take a closer look at the Jupyter notebook, we have defined the BIRCH method. The BIRCH method identifies the number of clusters to map. It can also be set manually. We have set branching underscore factor, number of clusters, and threshold parameters. The branching factor defines the number of subclusters and threshold sets the limit between the sample and subcluster. If you go a little upwards, you can see that we are taking into consideration only the annual income and spending score for implementing our model. After that, we'll fit our data into the model that we just now created. And for that, we are going to use the fit function. Now, as we can see, we have done the prediction on our data using the model that we created. For that, we have used the predict function. Finally, we are going to visualize the data using the scatter plot. Hooray! Now we'll understand Core clustering, the steps involved in it, and the phases of Core clustering. So let's begin. It is an efficient data clustering algorithm for large databases. It's more robust to outliers and identifies clusters having non-spherical shapes and size variances. Now you must be wondering, what does Core stand for? Core stands for clustering using representatives. Yes, I know it sounds quite simple. Let's try to understand Core clustering in depth and get a better understanding now. Core clustering is a hierarchical-based clustering technique that adopts a middle ground between the centroid-based and the all-point extremes. Now that we know that is clustering using representatives, let's take a closer look at Core clustering employs a fixed number or representative points to describe the cluster. And the set of representative points are first chosen randomly and then are shrunk towards the mean of the cluster. This shrinking operation plays a key role in Core, which is used for weakening the effect of outliers. Now, by taking a closer look at the image, let's try to understand Core clustering in a step-by-step approach. Now that we already know what are the steps involved in pure clustering, the next big question is, how does pure clustering work? Let me answer this for you. Beginning with the first phase is the initialization in pure. We'll take a small sample data, cluster it in main memory using hierarchical clustering algorithm. Then we will select a small set of points from each cluster to be representative points. These points should be chosen to be as far from one another as possible. Next, we'll move each of the representative points in a fixed fraction of the distance between its location and the centroid of its cluster. The fraction could be about 20% or 30% of the original distance. And the last one is completion of pure algorithm. Once initialization is complete, we have to cluster the renaming points and output the final cluster. The final step of pure is to merge two clusters. If they have a pair of representative points, one from each cluster that are sufficiently close, we may pick the distance threshold. We can repeat the merging step until there are no more sufficiently close clusters. Each point P is brought from secondary storage and compared with the representative points. We assign P to the cluster of the representative point that is closest to P. Now we are going to implement the pure clustering algorithm on the e-commerce data set. For that, we'll have to get back to our Jupyter notebook. First, we'll start by loading the important modules. Here we are going to install the Pi clustering module along with the other modules. After it's imported, let's do the data analysis and pre-processing and start exploring the data set. Next, we are going to plot the outliers in the data. As you can see, we have used a box plot for that. Let's remove the null values and filter the data set on the quantity to be positive. You can now see the shape of the data set 397921, 9. This means there are 3,97,921 rows and 9 columns after removing the null values. Now we'll visualize the quantity using a box plot. Let's take a closer look at the contribution of the countries on the data set. We are going to visualize this using a count plot. From the plot, we can see that customers from the UK are mainly utilizing e-commerce mediums at a significant level. We will select UK for performing the clustering analysis due to the sample size. Now let's create the matrix per customers for doing the customer segmentation. Now that the customer segmentation is done, we'll run this project based on how many times the customer bought something, average price of the items that they buy, and quantity per purchase. For doing that, the first thing we'll do is grouping the data using the customer ID, country, and aggregate of invoice number, stock code, unit price mean, sum of quantity. And we're going to find out the average of the items. After that, we'll keep only the invoice number, unit price, and average items in the data set. Now using the LOC attribute, we will select only the average items, outliers, and after removing the outliers, let's see our data. You can see there are 3,698 rows into 3 columns. Now we'll scale our data using the standard scaler. Finally, we are ready to implement pure clustering analysis. For doing that, we'll specify the number of clusters, path, number of representation points. And we're going to use the cluster visualizer function to visualize the data after performing pure clustering. We have successfully carried out data mining on our data set using pure clustering. Now let's quickly learn and understand the working of another important clustering algorithm, mini-batch k-means clustering algorithm. The big question is, if we already know how to use and implement the k-means clustering algorithm, then what is the use of learning mini-batch k-means algorithm? Let me answer this for you. When the data sets being analyzed increase in size, the computation time of k-means increases because it requires the whole data set in main memory. For this reason, a different approach is the mini-batch k-means algorithm. Each one of the algorithms are special in their own way, hence it's good practice and learn new algorithms. It'll improve your reasoning capability while performing clustering analysis. So without wasting any more time, let's get started and understand the mini-batch k-means clustering algorithm. The mini-batch k-means uses mini-batches to reduce the computation time while still attempting to optimize the same objective function. So let's try to understand what are mini-batches. Mini-batches are subsets of the input data randomly sampled in each training iteration. These mini-batches drastically reduce the amount of computation required to converge to a local solution. Now let's try to understand the mini-batch k-means in a step-by-step way. In the first step, samples are drawn randomly from the dataset to form a mini-batch. Then these are assigned to the nearest centroid. In the next step, the centroids are updated. In contrast to k-means, this is done on each sample basis. For each sample in the mini-batch, the assigned centroid is updated by taking the streaming average of the sample and all previous samples assigned to that centroid. By taking a closer look at the image, you can see the runtime is quite less for mini-batch k-means clustering. Although mini-batch k-means converges faster than k-means, still the quality of results is reduced. But in practice, this difference in quality is quite small. I hope you understood how mini-batch k-means clustering works and are excited to implement this too. Now, understand implementation of mini-batch k-means clustering algorithm. And for that purpose, we are again going to use the mall dataset. Again, we'll perform clustering on the annual income and spending score columns. As we have decided to create the clusters using the spending score, the annual income of the customers also, let's visualize the relation between these two characteristics of a customer using a scatter plot available in the Seaborn library. Now, by taking a closer look at the scatter plot for annual income versus spending score, we can see that there are 5 clusters visible. In k-means clustering, we had already learned why we use the elbow chart. Next, we'll start by preparing our data for analysis. Then we'll create a set of data which will only consist of the columns that we want to use for our analysis. As you can see, by using the drop function, we'll drop gender and age columns. Now it has 2 columns, that is annual income and spending score. Next, we'll find the optimal number of clusters by using the elbow method. Elbow method calculates the within cluster sum of squared errors for different values of k and chooses that value of k for which the WSS value starts to diminish in the plot of WSS versus k. This is visible as an elbow. To implement elbow method, we'll import the k-means algorithm from the sklearn.cluster module. Next, we'll create an empty list for storing the WCSS values. We will iterate from 1 to 15 to obtain the best value of k. Finally, our elbow chart is ready. As we've already discussed how to choose the best value for k, from the elbow chart, we can see that the last elbow occurs at 5. Hence, the optimal number of clusters for our analysis will be 5. Now, let's implement our mini-batch k-means clustering analysis. This time, we'll specify the n clusters parameter with 5 and rest of the parameters will be as it is. Now, to get the clusters, we'll use the fit function and store our results in a variable called mbk underscore means. Let's visualize these clusters by using a scatter plot. Here you can see we have 5 different values for mbk means, which are 0, 1, 2, 3, 4. These are nothing but labels for the 5 different clusters that we have just created using our mini-batch k-means clustering algorithm. For the x-axis, we are specifying annual income, which is encoded as 0, and the spending score, which is specified in the y-axis, encoded as 1. Finally, we have specified different colors for different clusters to identify them easily. Now let's discuss the inferences which we get from this plot. Mini-batch k-means converge faster than k-means, but the quality of the result is reduced, although this difference in quality is quite small. Next topic, introduction to mean shift clustering. To begin with, the most important thing is it is an unsupervised clustering algorithm that groups data directly without being trained on labeled data. The nature of the mean shift clustering algorithm is hierarchical in nature, which means it builds on a hierarchy of clusters step by step. Now you must be wondering, after learning so many clustering algorithms already, again, why we need to understand mean shift clustering? Let me answer this for you. Unlike the popular k-means cluster algorithm, mean shift does not require specifying the number of clusters in advance, and the number of clusters is determined by the algorithm with respect to the data. Mean shift algorithm basically assigns the data points to the clusters iteratively by shifting points towards the highest density of data points, that is cluster centroid. Now let's discuss some of the pros and cons of the mean shift clustering pros. Mean shift is quite better at clustering as compared to k-means, mainly due to the fact that we don't need to specify the value of k, that is, the number of clusters. Output of mean shift is not dependent on initialization. The algorithm only takes one input, the bandwidth of the window. Cons? Mean shift performs a lot of steps, so it can computationally be expensive with a time complexity of n squared. The selection of the bandwidth itself can be non-trivial. If the bandwidth is too small, enough data points may be missed and convergence might never be reached. If the bandwidth is too large, a few clusters may be missed completely. The mean shift clustering algorithm can be computationally expensive for large data sets because we have to iteratively follow our procedure for each data point. Last but not the least, let's see some of the applications of the mean shift clustering. Mean shift clustering algorithm is mainly applied in computer vision problems. Popular applications include image processing, video tracking, image segmentation. As we already know, as it is a clustering algorithm, our final goal is to represent this unordered data in an organized way and divide it into clusters. Mean shift essentially starts off with a kernel, which is basically a circular sliding window, and the bandwidth, that is, the radius of this sliding window, that can be pre-decided by the user. Now let's try to understand the mean shift clustering using a step-by-step approach. Firstly, we have to pick any random point and place the window on that data point. And now, moving on to the next step, that is step number 2. We have to calculate the mean of all points lying inside this window. Coming to step 3, we'll shift the window such that it is lying on the location of the mean. Finally, we'll repeat till convergence. What we are trying to achieve here is to keep shifting the window to a region of higher density. This is why we keep shifting the window towards the centroid of all the points in the window. This feature of mean shift algorithm describes its property as a hill climb algorithm. And now we must iteratively go from lower density to higher density regions in order to find our clusters. This is exactly what we aim to achieve with the mean shift algorithm. Iteratively finding the high density regions and shifting our window in that direction until we reach convergence. For last few points, we've been using the word convergence. Let's understand what does convergence exactly mean. The mean shift algorithm proceeds step 1 to 4 as we have already discussed, and then finds a final window location for each of the data points. For each iteration, we find the centroid of all the points in the window, shift the window accordingly, and repeat. However, after a sufficient number of steps, the position of the centroid of all the points and the current location of the window will coincide. This is when we reach convergence, as no new points are added to our window in this step. Now we'll see the implementation of mean shift clustering. Again, we'll perform clustering on the annual income and spending score columns. We'll start by loading the important modules. First, we'll import unique function of numpy module. Next, we'll import mean shift from sklearn.cluster. Now we'll create mean shift clustering model. And we are keeping the bandwidth as 25, neither too big, neither too small, so that no data points are missed and convergence can be reached. Then we'll fit our data X around the model we created using fit function. Next, we'll use the predict function to predict the number of clusters. Next, we'll find out the exact number of clusters using the unique function. Then, we'll determine the centroids of the clusters, which is very important for mean shift clustering. As you can see, clusters of mean shift is 0, 1, 2, 3, 4. Now we know the number of clusters. As we have created the clusters using the spending score and the annual income of the customers, let's visualize the relation between these two characteristics using a scatter plot available in the Seaborn library. Here you can see the centroid of the clusters in red color and all the clusters of data 0, 1, 2, 3, 4 that we have predicted. For the x-axis, we are specifying annual income and the spending score, which is specified in the y-axis. Now let's discuss the inferences which we get from this plot. Mean shift clustering do not require specifying the number of clusters in advance. The number of clusters is determined by the algorithm with respect to the data. Let's understand the optics clustering algorithm. First of all, optics stands for ordering points to identify cluster structure. The most important thing is that optics is a hierarchical density-based data clustering algorithm that discovers arbitrary shaped clusters and eliminates noise using adjustable reachability distance thresholds. Now let's go into the depth about optics clustering. For doing that, we need to do a little recap of DBSCAN algorithm. The DBSCAN algorithm has two parameters, which are EPS and midpoints. The EPS parameter in the DBSCAN algorithm specifies how close points should be to each other to be considered a part of a cluster. Now this means that if the distance between any 2 points is less than or equal to the EPS value specified by us, it will be considered as neighbors. This EPS value will act as a threshold for considering 2 points as a neighbor. Let's take a look at the second parameter now, which is min points. This parameter is used to specify the minimum number of points to form a dense region. Now the big question is, when we already have so many amazing clustering algorithms, why do we need optics clustering? Let me answer this for you. Optics is a clustering algorithm that is an improvement of the DBSCAN algorithm. Optics can find clusters of varying density as well, which DBSCAN was not able to do due to fixed EPS. Now let's look at some of the important parts of optics clustering. And as you can see, the first is core distance. It's the minimum value of radius required to classify a given point as a core point. If the given point is not a core point, then its core distance is undefined. The next one is reachability distance. Is defined with respect to another data point, Q, let. The reachability distance between a point P and Q is the maximum of the core distance of P and the Euclidean distance or some other distance metric between P and Q. Please note that the reachability distance is not defined if Q is not a core point. And the optics clustering technique is different from other clustering techniques in the sense that this technique does not explicitly segment the data into clusters. Instead of segmenting the data directly into clusters, it produces a visualization of reachability distances and uses this visualization to cluster the data. So let's get started and look at the main differences between these two clustering algorithms. DBSCAN and optics are two of the most well-known density-based clustering algorithms. The key parameter to DBSCAN and optics is the min PTS parameter. It roughly controls the minimum size of a cluster. If you set it too low, everything will become clusters. If you set it too high, at some point there won't be any clusters anymore, only noise. Optics with min points is equal to 2 degenerates to a type of single link clustering. As you already know, that the more difficult parameter for DBSCAN is the radius. And in some cases, it will be very obvious. Say you're clustering users on a map, then you might know that a good radius is 1 kilometer or 10 kilometer, whatever makes sense for the particular application. In other cases, the parameter will not be obvious, or you might need multiple values. That is when optics come into play. Optics is based on a very clever idea. Instead of fixing min points and the radius, we only fix min points and plot the radius. Now let's look at a few major differences between optics clustering and DBSCAN clustering. Optics come at a cost compared to DBSCAN, largely because of the priority heap, but also as the nearest neighbor queries are more complicated than the radius queries of DBSCAN. So it'll be slower. But you no longer need to set the parameter epsilon. Optics clustering does not segregate the given data into clusters. It merely produces a reachability distance plot. Let's have a look at the implementation optics clustering part now. To begin with, we'll make all the important imports. Now we'll make use of make_blobs for generating the data, optics for clustering, and NumPy and matplotlib for numbers processing and visualization respectively. Next, we'll be specifying a range of configuration options. We'll generate 1000 samples in total around 2 centers so that we'll get 2 blobs of data. Then we'll set epsilon and min samples to values that we derived during testing, as well as a method for clustering and the distance metric. The values for cluster method can be SHE and DBSCAN. The values for cluster method can be XI and DBSCAN. With XI, a cluster-specific method can be used for extracting clusters. With DBSCAN, a fixed threshold can be used for extracting the clusters from the reachability plot. Many metrics can be specified under metric. The Minkowski distance is the default one. You can look up sklearn for that here. Now that our configuration is done, we'll generate the data, that is 2 blobs of data with make_blobs. But before moving forward, let's understand a bit about the make_blobs function. Make_blobs create multi-class datasets by allocating each class one or more normally distributed clusters of points. Make_blobs provides greater control regarding the centers and standard deviations of each cluster and is used to demonstrate clustering. Based on this data, we'll perform optics-based clustering with epsilon, minimum number of samples, cluster method, and metric defined. We'll immediately fit the data so that the clusters are generated. Now we'll print the estimated number of clusters and the estimated number of noise points. Finally, we'll generate a scatter plot for our data. Next, we'll also generate our reachability plot, which is an important part of optics clustering. Now, let's discuss the inferences which we get from this plot. Optics works by ordering based on reachability distance, while expanding the clusters at the same time. The output of the optics algorithm is therefore an ordered list of reachability distances, which by means of thresholds or different techniques, we can split into clusters. This way, we are able to generate clusters for groups of data that have varying densities. Now, let's come to the next topic, spectral clustering. You must be thinking, after learning so many clustering techniques, what is spectral clustering? Well, in recent years, spectral clustering has become one of the most popular modern clustering algorithms. It's simple to implement, can be solved efficiently by standard linear algebra software, and very often outperforms traditional clustering algorithms, such as the k-means algorithm. Now let's try to understand spectral clustering in depth. Spectral clustering uses the connectivity approach to clustering, wherein the communities of nodes, that is the data points which are connected or immediately next to each other, are identified in a graph. After that, these nodes are mapped to a low-dimensional space that can be easily segregated to form clusters. Spectral clustering uses information from the eigenvalues, spectrum of special matrices, that is affinity matrix, degree matrix, and Laplacian matrix, derived from the graph or the data set. Unlike the conventional clustering algorithms, spectral clustering algorithm methods are attractive, easy to implement, reasonably fast, especially for sparse data setups to several thousand. Spectral clustering treats a data clustering as a graph partitioning problem without making any assumption on the form of the data clusters. Now that we have the basic idea about spectral clustering, let's look at some applications of it as well to get a better idea about where we are going to use it. Spectral clustering has its application in many areas, which includes image segmentation, educational data mining, entity resolution, speech separation, spectral clustering of protein sequences, text-image segmentation. The big question is, why do we need spectral clustering even after having so many other clustering techniques already? One of the main fields in machine learning is the field of unsupervised learning. The main idea is to find a pattern in our data without the prior knowledge of labels, as in supervised learning. It's usually achieved by clustering our data into groups and trying to infer meaning from the clusters. One of the more popular algorithms is the k-means algorithm. In this algorithm, we have k-centroids adjusted in an iterative process to find our clusters. Sounds good, right? But the main problems are, it makes assumptions on the shape of the data, a round sphere, or radical basis. It requires multiple restarts at times to find the local minima, that is, the best clustering. Spectral clustering algorithm helps to solve these two problems. This algorithm relies on the power of graphs and the proximity between the data points in order to cluster them, making it possible to avoid the sphere-shaped cluster that the k-means algorithm forces us to assume. Now, if you remember, we had already discussed that spectral clustering uses information from the eigenvalues, that is, spectrum of special matrices, which is affinity matrix, degree matrix, and Laplacian matrix, derived from the graph or the data set. Now, let's try to understand them one by one. Starting with the first one, that is affinity matrix, is like an adjacency matrix, except the value for a pair of points expresses how similar those points are to each other. If pairs of points are very dissimilar, then the affinity should be 0. If the points are identical, then the affinity might be 1. In this way, the affinity acts like the weights for the edges on our graph. Now, the second most important one is the degree matrix. Degree matrix is a diagonal matrix where the degree of a node of the diagonal is given by the number of edges connected to it. We can also obtain the degree of the nodes by taking the sum of each row in the adjacency matrix. Finally, the last one is the Laplacian matrix. Laplacian matrix is another representation of the graph or data points, which attributes to the beautiful properties leveraged by spectral clustering. One such representation is obtained by subtracting the adjacency matrix from the degree matrix to gain insights and perform clustering. The eigenvalues of L are used. Some useful ones are mentioned here. Spectral graph, The first non-zero eigenvalue is called the spectral gap. The spectral gap gives us some notion of the density of the graph. Fiedler value. The second eigenvalue is called the Fiedler value, and the corresponding vector is the Fiedler vector. Each value in the Fiedler vector gives us information as to which side of the decision boundary a particular node belongs to. Using L, we find the first large gap between eigenvalues, which generally indicate that the number of eigenvalues before this gap is equal to the number of clusters. Now you must be wondering that how we are going to do the spectral clustering. Let's look at the steps involved in spectral clustering. The three major steps involved in spectral clustering are constructing a similarity graph, projecting data onto a lower dimensional space, and clustering the data. Given a set of points S in a higher dimensional space, it can be elaborated as follows. Form a distance matrix. Transform the distance matrix into an affinity matrix A. Compute the degree matrix D, and the Laplacian matrix L is equal to D minus A. Find the eigenvalues and eigenvectors of L. With the eigenvectors of K, largest eigenvalues computed from the previous step form a matrix. Normalize the vectors. Cluster the data points in k-dimensional space. Now we are going to implement the spectral clustering algorithm, and for that purpose we are going to build a spectral model with Python and scikit-learn. To begin with, we'll make all the important imports. We'll make use of make blobs for generating the data, random function for generating random numbers, and numpy and matplotlib for numbers processing and visualization respectively. Next, we'll start with preparing our data and build our spectral clustering model on it. For that purpose, we'll use the random.seed function to generate random numbers and to save the state of a random function so that it can generate the same random numbers on multiple executions of the code on the same machine or on different machines for a specific seed value. Next, we'll generate the data that is with make blobs. Then, as you can see, we're going to visualize our generated data using a scatter plot. Based on this data, we'll perform spectral clustering with the minimum number of clusters, cluster method, or other matrix defined. In the matrix, we can clearly see the use of eigenvalues and affinity matrix. We will immediately fit the data so that the clusters are generated. As you can see from the output, we will print the number of clusters. Finally, we'll generate a scatter plot for our data, discussing the inferences which we get from this plot. Spectral clustering does not make any assumption on the form of the data clusters. Now we are going to learn and understand the working of a powerful clustering algorithm, the Gaussian mixture clustering algorithm. The first and foremost important thing is that Gaussian mixture models, that is GMMs, assume that here are a certain number of Gaussian distributions, and each of these distributions represent a cluster. Hence, a Gaussian mixture model tends to group the data points belonging to a single distribution together. When hearing of this technique, you may have thought about the Gaussian distribution, also called normal distribution. That's exactly what this clustering technique is based on. The first question you may have is, what is a Gaussian? It's the most famous and important of all statistical distributions. A picture is worth 1,000 words. So here's an example of a Gaussian centered at 0 with a standard deviation of 1. It assumes that the data points come from multi-dimensional Gaussian distributions that could have varying parameters of covariance, mean, and density. And another very important thing is that Gaussian mixture models work based on an algorithm called expectation maximization, or EM. So let's take a closer look at EM. When given the number of clusters for a Gaussian mixture model, the EM algorithm of these Gaussian distributions in a step-by-step approach, we'll see. The first approach, the E step, that makes a guess of the parameters based on available data. Data points are assigned to a Gaussian cluster and probabilities are calculated that they belong to that cluster. The second step is the M step that updates the cluster parameters based on the calculations from the E step. The mean, covariance, and density are calculated for clusters based on the data points in the E step. And lastly, the process is repeated with the calculated values continuing to be updated until convergence is reached. If you're familiar with k-means, this process at a high level is really the same. Now let's discuss the key differences between Gaussian mixture clustering algorithm and k-means clustering algorithm. To begin with, the Gaussian mixture models can be used to cluster unlabeled data in much the same way as k-means. There are, however, a couple of advantages to using Gaussian mixture models over k-means. First and foremost, k-means does not account for variance. By variance, we are referring to the width of the bell-shaped curve. Now, in 2 dimensions, variance, covariance to be exact, determines the shape of the distribution. And one way to think about the k-means model is that it places a circle, or in higher dimensions, a hypersphere, at the center of each cluster, with the radius defined by the most distant point in the cluster. This works fine for when our data is circular. However, when our data takes on different shapes, then we end up with something like this. And on the contrary, Gaussian mixture models can handle even very oblong clusters. Well, that was all about the first major difference between the Gaussian mixture clustering and the k-means clustering. Now let's take a close look at the second key difference. The second key difference between k-means and Gaussian mixture model is that the former performs hard classification, whereas the latter performs soft classification. In other words, k-means tells us what data point belong to which cluster, but it won't provide us with the probabilities that a given data point belongs to each of the possible clusters. So now we'll implement the Gaussian mixture clustering algorithm. And for that purpose, we're going to build a Gaussian mixture model with Python and scikit-learn. But before implementing, we must have the basic knowledge about AIC and BIC are 2 most popular evaluation metrics for picking cluster numbers for fitting Gaussian mixture models. Let's start with BIC. It stands for Bayesian Information Criterion, and AIC stands for Akaike Information Criterion. The intuition, the purpose in calculation of both of these metrics is that they favor the simplest model that maximizes the likelihood function of the model. And calculating the AIC and BIC is easy because they are built in as a method on the scikit-learn Gaussian mixture class. Now that we have a grasp of how Gaussian mixture model works, let's take a look at how we are going to implement them. To begin with, we'll make all the important imports. Now we'll use make blobs for generating the data, Gaussian mixture for clustering, NumPy for number processing, matplotlib and seaborn for visualization. Next, we'll generate 4 clusters using the makeblobs function. Next, we'll be specifying a range of configuration options. We'll generate 300 samples in total, around 4 centers, so that we'll get 4 blobs of data. Now that our clusters are generated, let's visualize them using a scatter plot. The optimal number of clusters is the value that minimizes the Akaike Information Criterion or the Bayesian Information Criterion. Next, we are going to plot the AIC and BIC to find the optimal value of K. From the plot, we can see that the AIC and BIC are differing by a significant margin. And when they differ, BIC more heavily favors simple models than AIC. Now that BIC and AIC are plotted, we'll train our model using the fit function and using the optimal number of clusters. In this case, that is 4. After training our model, we'll use the predict method to obtain a list of points and their respective clusters. Next, we'll visualize our data using a scatter plot. Let's discuss the inferences which we get from this plot. Unlike k-means, Gaussian mixture models account for variance and return the probability that a data point belongs to each of the k clusters. Great! We are done with implementing the Gaussian mixture clustering. Now let's discuss the working of the kernel density estimation. The first and foremost thing is that kernel density estimation is a process of estimating an unknown probability density function using a kernel function. While a histogram counts the number of data points in somewhat arbitrary regions, a kernel density estimate is a function defined as a sum of a kernel function on every data point. Along with that, kernel density estimation is a useful statistical method to estimate the overall shape of a random variable distribution. In other words, kernel density estimation helps us smooth and explore data that doesn't follow any typical probability density distribution, such as normal distribution, binomial distribution, etc. As we have already discussed, KDE for the whole data set is obtained by adding all row values. The sum is then normalized by dividing the number of data points. Normalization is done to bring the area under KDE curve to 1. Therefore, the equation to calculate KDE is expressed as where n is the number of data points. Now, let's try to understand KDE with the help of an image. From the plot, we can see the KDE after adding all normalized kernels. Let's implement the kernel density estimation. And for that purpose, we are going to use the TED Talks data set. So before directly jumping onto our Jupyter notebooks, let's understand KDE a little bit more. Kernel density estimation are a family of methods for estimating underlying densities. In this lecture, we'll take a quick look at their properties and discuss why they are useful using TED Talks lens. Kernel density estimation is useful in particular because it is non-parametric. What that means is that KDEs do not rely on any assumptions about the shape of the underlying data. They are based solely on observed properties of the data. To demonstrate, let's look at the simplest non-parametric density estimation method, a histogram. In this plot, we see that the vast majority of TED Talks are under 1200 seconds, which is 20 minutes, peaking at around the perhaps 18-minute mark. In general, histograms are a very useful exploratory technique. However, they suffer from two major shortcomings. The first is that the look of a histogram depends a lot on where you place the bin edges. They tend to work well for normal distributions, but tend to fall apart for more complicated things. The second is that it requires a lot of samples and furthermore requires roughly twice the number of samples to get roughly twice the accuracy. These limitations make the data harder to interpret. A KDE smooths them over by interpolating, by coming up with logical values to fill in gaps between points in the data. For example, here is the KDE plot for this data using Seaborn. We can see how much clearer this view of the data is. It shows that TED Talks actually peak in duration at around 1000 seconds. We can even see what might be an interesting substructure at around the 5-minute mark. Kernel density estimates do this by computing a density for every space of points in the distribution. That density is a function of the data points that are near that point in space. Roughly speaking, data points near the theoretical point are important in determining the value of that point, while data points further away are given less value. After a certain cutoff, points no longer have any influence on the density estimate. The points that end up being used for the estimate are blended together using a function known as a kernel. The cutoff points used to build the estimate is controlled by a hyperparameter known as the bandwidth. By using a kernel with a given hyperparameter to make an estimate of density at every point of interest on the curve. We build a kernel density estimate for the entire distribution. So, for example, if you take a point, say 1300 seconds, took every point within 100 seconds of that point, and took the average of those points, that would be an example of a simple kernel density estimate. In practice, the simplest kernel that tends to get used is the Gaussian kernel. We just discussed an example of that, but here's another one that's more demonstrative of the effect that bandwidth has on the output. The blue KDE is a Gaussian estimate with a bandwidth of 10. The orange KDE is a Gaussian estimate with a bandwidth of 40. The 10 bandwidth KDE shows us more interesting features of the data, like the fact that speeches are significantly more likely to be 10-minute long than 9-minute long. But it also demonstrates more variance than the far smoother 40 bandwidth KDE. In fact, this is what choosing a bandwidth is all about, making a trade-off between bias and variance. The 100 bandwidth curve, for example, is starting to look too biased. It misses. For example, the height of the peak of the data around the 1000 second mark. Note that KDE produces probability distributions, not functions. Great. Finally, we are done with kernel density estimation. And here we come to an end of this clustering analysis full course. We have covered all important concepts in this course. Hope you guys enjoyed it. And if there are any suggestions, please go ahead and comment them as well. We'll try our best to reply to each of your comments. Goodbye, and don't forget to subscribe to our channel for more informative as well as fun videos like this.